All right, so yeah, I GameState discretization. Like if you look at the notes, because I got kind of tired last stream, and I think this will be pretty short too. Actually, we'll see. But like last time, let me open up the notes. I had a plan where I basically like did all of this stuff, and then like today, like I want to like maybe not complete this, but at least like give it some treatment. Like at least give a high level discussion about game state discretization, like convert to image stack, right? Like given a game state, like for Connect 4, you have like two image stacks. Like we have an image stack of two image planes, where each plane, like the top plane is the current player's coin coordinates, a binary 0, 1 entry. The I comma jth coordinate like is 1 if and only if there is a cell occupied or a coin at that coordinate by that player. So like Connect 4 is nice and discrete because like all the values are like between columns 0 through 6 because there's 7 columns, right? And like there's like it's like a fixed row and like the coordinates are basically fixed, right? In Connect 4, whereas in BumperCoins they're floats. Well, not floats, they're fixed point numbers. That means like there's a decimal value. Like it's not like all discrete numbers. It's not all clean round integers. It's they can be fractions, right? So like we have to do some rounding to pass it into a neural network, right? So then like that's basically like the idea right now for the discretization. And also one thing I'd like to add about last stream was I think I got like 0.405 or like some number corresponds to 1 second, because my idea is like instead of like taking the 0.4 and like given the strength derive the frequency, like I was like maybe I should start off with the frequency as 1 second between moves and like derive the strength that corresponds to. But you know what I realized? Like 0.4, I think like if you kind of like work out the actual like ticks it takes about like what was that? Whiteboard. Yeah, okay, wow. This is such good, this is like such a good, like, okay, I'm glad I didn't close this tab. Right, like 59.2, right? If you take 59.2, wait, what the hell? 59.2 and multiply that by 60, right? By 60, that's where you get like, what? Sorry about that. 59.2 divided by 60. And then like you get like 0.9866, which is familiar from a previous stream. And like that's how much of a second it takes. So like basically like if you launch a coin at 0.4 times max intensity, then this takes 59.2 it'll take 59.2 ticks to replenish, right? But that means technically we have to round up because a tick is like it's a tick. You can't have like a fraction, you can't have 0.2 of a tick, right? So nice thing about using 0.4 max move strength is approximately like the key thing is it is strictly greater than 60, but it comes close. So like, and yes, fixed point does add some more approximations, but I'm pretty sure that like it should be like 59 basically, point something. So like the point is that 60 is an upper bound. So like if we kind of like at the end of last stream, I remember I edited the description. Like I edited the description of the stream to be gave it a quick summary of like the plan moving forward for implementation. And like this is kind of the idea. 60 ticks between each player's successive moves, which works out to be 1 second because it's a 60 FPS game. So basically, here's how like it works. Like these are like the two while loops. Like while the game has not ended, move for the player's turn it is. That means select a coin and launch at this, instead of approximate, let's just make it exactly 0.4 times max launch. And by doing so, we know that it'll take 59 ticks to around 59 ticks, technically 60 to consume. Like after 59 ticks, we're 98% of the way there, or like, yeah, after 59 ticks, we're so close to being replenished. And then we just need one more. But then like, since we're already so close, one more will really put us over the finish line. So we have lots of room to spare, which means that by 60 ticks, like after we make that move and wait 60 ticks, it must be the case that we have reached the level we were at least the level we were at when we first made the move. And then if we're like starting off at full strength, right, which is an upper bound clamp, like if we're at full energy, we can never exceed it. Therefore, I propose that we can exactly do 0.4 and see how it works. In fact, this number, technically, like because of discretization, this does have some implications for 0.4, this number. So I do have to check, like, for example, like let's just say that like we have like, let's just say that it's a 2x2 grid or whatever, and we have a coin here, and we launch it at like 0.4 intensity, and then like it has to go to the next cell, right? But like what if after launching it, that's a very weak launch, and we end up here, right? Then like after discretization, like the discretization will look like this. It'll be like 1, 0, 0, 0. And like after we do the launch, we really want it to look like 0, 1, 0, 0, right? But if like that means it has to kind of cross this like special line here. But let's say it lands here, right? Like what if 0.4 is not enough? I'm pretty sure it's enough, actually. I'm really sure, because I remember we saw that a full launch corresponds to either 6 or I think like 6 or 8 or something cells. I mean, yes, it's not linear. It's like there's some decay, like exponential decay or something, like due to like the way friction's implemented, or not friction. Yeah, friction or acceleration. Yeah, instead of like doing actual like mathematical acceleration, well, forget it. I have like a geometric acceleration, like multiply the speed by 0.9 each tick, so it's non-linear. But I'm sure but anyways, the point is that like, let's say that like, basically because of discretization, right? Like if we have like, actually, why am I drawing grids? I can literally like recycle a grid that already exists, right? As a 2x2 grid, like this line here and that line there. So like, if we have a coin here, then this basically, like if this is our coin, like if this is the center of our coin here, right? Like dot, 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 then this coin, after being discretized, maps to that, right? But then what if the coin is here, right? Like what if this is our coin now? Like this is our second coin. Like that's like 1, and that's like 2. Where like a coin can be specified fully by its radius. I mean, by its center coordinates, because the radius is like about 1. I mean, it's exactly 1, I think. Is it? Well, it doesn't matter. The point is that coins can be fully specified by their center coordinate, and then like there's like a static variable and probably shared constants or something. Not in shared constants in coin. The point is that the center coordinates matter, and like, yeah. So like you take this box here, right? Like when you're converting it into like discrete, the point is that like this coin centered here and the coin centered here, they will both map to this one. Only once the center like crosses, or let's just say like, let's see, the moment it hits this vertical line, then like if you're in this bin, let's just say like, I like this kind of like math type convention where like the left is inclusive and then the right bound is exclusive, like inclusive and exclusive, like open, like the bracket means inclusive and then the paren means exclusive, right? So if you're in this bin, then you kind of map to this one, right? But then like what if like after moving from like this one, we kind of hit a new point in 2, like our coin basically after moving, like what if we land here, right? Then like we kind of like, we really want like the state to change. Like when we're doing the actual Monte Carlo tree search, right? Like we take a game state, we take the UCB score, we take the most promising action, and then we basically build a search tree, right? But then like we really want to see this this progression right here. We really want to like see that happen in the tree state. Like we don't want to like stay in the same state. That's why when we're discretizing it, like let's just say like one option instead, I think it should be an odd number actually, is like if this is our actual, like if it's a 2x2 thing, like if it's like that, right? Like what I can say is like we can kind of like add like a dotted line. Like we can basically like, let's say like our discretization factor is 3, right? Let's call it DF, just discretization factor. Then like every single cell like in like our grid is going to basically like have 9, right? It'll have like discretization factor DF squared entries, right? So then like, so basically like if this is the case and like we have like a coin, like 1 could be like right here and like 2 could be here, then like in this case it would be a bit different, right? Like now, like you'd have like, and so forth. So like now basically like what I'm saying is like if you have like coin 1, like the first coin here, the second coin here, after launching it, you still stay in the same grid cell. Like in this if this is discretization factor of 1, right? Like this is 1 and this is 3, right? So in here, like you would kind of go from like this thing, like from 1 and 2, starting here, you'd basically kind of end here. And it doesn't, like, you don't see the progression, right? Whereas like here, what would happen is like you would basically like go from this 1 and everything else zeros to same 2 by 2 stuff. But the whole point is that like this one here, like this one is now a 0, and this 0 here is now a 1. So like it's showing the progress. That's why, I mean, I'm pretty sure discretization factor of 1 should work. I'm really confident of that, like based on like playing around in BumperCoins, but we'll see, right? We'll see. So let's just say, I mean, I think I want to do everything in general, like df equals 3, like here in this case, and like here df equals 1. So the question is like, how do we actually actually implement this, right? So like, again, like here what we can just do is like math.trunc, right? Math.trunc, like truncate the fraction component and only leave the whole number behind, right? Like let's just say like basically like this bucket, right? Like this range right here, like this thing right here, right? Like the range to get into like, let's think of x-axis, like let's think of like this axis right here, then to like land like here, like to land in this thing right here in this first cell, you need to be between what? Like what is our like start and end, right? Our interval, like our bucketing strategy for this is 0 inclusive and 1 exclusive, right? And then for this one, we can pretend it's a number line, like we're not using the y direction at all. Then for this one, it would be 1 inclusive, and then 2 would be exclusive, right? So anything in this interval, like right here for x coordinate or whatever coordinate here, gets mapped onto this one, right? But whatever that lies in this coordinate right here, actually, why do I have these circles? Whatever lies in this one between 1 inclusive and 2 exclusive lands in there. So like 1.1, we truncate the decimal and we get 1, which is correct because this is 0 index and this is 1 index, right? So here, let's say we have like 0.99, right? But if we truncate that truncates to basically 0, which means like we're right in the borderline, but we're not quite there, so we still map to 0. And again, like 0.5, a nice midpoint. Clearly, when we like truncate that, we get 0, right? So then 0 is the correct index. Now for here, right? So now like in this case, like, so now if df is 3, right? Then what's the formula? Like let's say we have our x to be like 0.5, and this one could be like 0.7. Now I'm saying that because like we know this line's at 0.666666 infinite, right? So now what are the buckets, right? The buckets are as follows. Like the buckets would be 0 and then 1/3. Or basically, yeah, and then you would have the next bucket would be that's too much. The next bucket would be 1/3 to 2/3, right? This reminds me of the probability thing. Remember when we were doing like the sampling with weights, that LeetCode question? Similar bucketing strats. So we have like this thing right here. as our second thing, and then from here to here would be 2/3, and then one exclusive, right? So basically, like this bucket right here from 0 to 1, we kind of expanded it out. We expanded the 0 to 1 bucket to have like 3 more buckets, right? That's what DF, discretization factor, is. That's kind of like the reasoning behind it, right? I mean, that's like the meaning of discretization factor, right? So given 0.5, 0.5 should map to what? Well, like this is bucket 0, like this is like 0 index, 1 index, and 2 index, right? Again, everything I'm doing is in like, let's call this like the x-axis, right, so to speak. Like it's in the same axis right here, this x-axis and that x-axis. Like again, like everything we're doing in this x-axis, we have to again do for the y-axis. And then like there's this notion of like 2 words come to my mind, right? Like when I think of like doing something for x and do something for y, and like just like 2 words come. Like one word is superposition, and second word is independence. Superposition. Sure, why am I writing this? I'm not like, yeah, but like it's the notion of superposition. Like we do it for one direction, we do it for the other. We just superimpose the like in physics, you have like x component, y component, you treat independently, and the answer is just like that, comma that. It's a common pattern. Like in like LeetCode questions, often like when you're given like a 2D grid or like a 2D question, like one good strategy like is think of the edge case where one dimension is like kind of fixed to 1, and like instead of a 2D grid, you solve it for an array, right? And then you try to generalize your answer for the 1D case to the 2D case. That's very often a useful technique, which just a useful problem solving method. But anyways, so 0.5, you want to map that to what? 0.5 belongs in 1, right? So this one, we like f of 0.5 should give us 1, right? Like we want this to map to 1 and this to map to 2. Why? Because 0.5 lies in this interval, and 0.7 is between 0.6666 infinite and 1.0. So that should be 2, right? So how do we do that? Well, okay. I mean, there it was super easy. We just did math.trunc to truncate it. But how do we do it for a general case, for DF3 in this case? So let's consider the midpoint, right? Like what's the midpoint like? So we have like this one, and then this one basically becomes like this one. So what if you consider the midpoints, right? Or actually, why are we doing grids? Let's just consider like a single array, right? Between like 0 and 1. Actually, no, let's just keep it there as grids. I was going to do a number line instead, but like... So we kind of have like 3 different centers. Like they're just one center, which is at 0.5. But now we have a center of what? Like 1/3 divided by 2 is 1/6. And then like 1/6 plus 1/3. And then like 1/6 plus 2/3. Or actually, no. Okay, so like right here, the crucial point is this line. That's the actual boundary. The moment we like hit it, then that. So the actual boundaries are like 1/3, 2/3, and just 1, right? Actually, I feel it's actually better to, instead of like have an example in like the top left corner, I think it might be a bit more like instructive to have something like this, like that. And we're doing the x coordinate for like this one, basically. So instead of 0.5, we have like 1.5. Like basically I'm taking these two numbers and I'm plus oneing them. I'm adding them to 1. So 1.5 would basically be like right here. That's 1.5. And then 1.7 basically kind of falls like about here, right? Or like, yeah, about here. Okay, we just multiply by 3, right? Like if we just do that by 3, right? And truncate? Wait, no, that's my intuition. Let me think. So in this case, what's the range, right? Like from that case, if you had 2 by 2, discretization, the range, like how many intervals do we have in like the 2 by 2 case with df1? Like we only have 2 buckets, like 0 to 1 and 1 to 2. Like that's 0, that's 1, right? But in this case, we have like 6, right? From 0 to 5, like 0, 1, ... 5, right? Yeah, we just multiply by that. Because like if I look at the 0.5, right? Like the 1 basically gets me all the way to this line. Because like 1 times df3, right? Gets me 0, 1, 2, and then like right here to the third boundary. And 0.5 times 3. So like this one, we do like 1.5 times 3, which is 45. I mean 4.5, right? Times 3, it's a 4.5. So that means like that means that like we have like the distance is like 0, like 1, 2, 3, 4, and then 0.5, and that's how we get this dot, right? And then same logic, we truncate it, right? And what's 1.7 times 3? Actually, no, let me first like clean this garbage I just wrote here. 1.7 times 3 is what? Well, like 21. So then for 3, 5.1. Yeah, 5.1. Okay, good. So like that would be like 1, like that's like 1, 2, 3, 4, 5, and then like a little bit more. So I guess this dot should have been placed a bit more there. But anyways, so 0, 1, 2, 3, 4, 5, and 0, 1, 2, 3, 4, and then trunk. So the general formula, right? The general formula, like given a chord C, like given a chord C, f of C returns a discretized coordinate discretized coordinate of C. Now this C could be an X coordinate or it could be a Y coordinate. We treat them exactly the same, right? Okay, technically some edge cases, because like number of columns and number of rows, if it's not a perfect square, if it's like a rectangle, like where length and width are different, then we might have to do some different bounds. But like the naive, like one thing is like basically like this one, my idea is that like we take C and like we multiply C by a df, and then, or sorry, and math.trunk that. Let me write it differently. So math. Actually, why am I writing math? Just do trunk of C times df, and that's it. So let's say that the coordinates of like 1.5 is 1, right? That means like 0 and 1. We just land directly here, right? Like that's the very borderline. So 1 times 3 is just 3. And then 3.0 truncate that is just 3. So it's 0, 1, 2, 3. So like indeed we get this. Because like the moment we hit that, like it's exclusive for 0 to that thing, but it's inclusive for that point is like, it's just like this whole like this convention of like, which I'm gonna adopt of, where's the SE nonsense I wrote? Yeah, this thing right here. Inclusive, exclusive, like that's kind of the convention. So like, so 1 correctly maps to 3, like 0, 1, 2, 3, it maps to this one, which is good, which is very good, right? Okay, now let's say we have 0.999, right? Times 3 is like, I don't know, like 2.98 or something. Point is, it'll be strictly less than, it'll be like almost there, but it'll still be like 0, 1, 2. And like when we truncate it, we'll get 2. So like 0, 1, 2, and we'll end up here in this cell for that. So like, yeah. Basically, like whatever discretization factor we're in, if we have like 2 things right here, and like as long as the center point like kind of lies in any of these dots, we kind of get this one. But the moment we cross over this magical threshold right here, which becomes like the new start for the next one, or like we go past the end for the previous one. Oh, why is my line there? Then like we suddenly like there's a huge jump between here to here, like a very drastic jump, because we escape the bucket, we're on the next level. So it's like 0.999 times 3, right? 0.999 times 3. Sorry about that. It's 2.997, right? So 2.997, and then we truncate the decimal, we're left with 2. So yeah, it works out. It works out. That's good. So that's basically it. This is basically, oh yeah, and also we should also do like, let's just say like, let's call this M. Or M, or let's call this U, where U equals upper bound, right? So basically, like then we have to do like X equals, and then X we have to like min and max them, right? Like X equals, just to be defensive programming, X is like the minimum of X and 0, just to like filter out any negative nonsense, which I don't think can be. And X equals the max, right? The max of X, comma U, the upper bound, right? Which means that like we can't go over U, right? Wait, no. What am I saying? This is the min. This is the min, and that's the max, right? Yeah, so like this is the min. Erase it. Where's my eraser? How do I erase things? Select. Delete. Select. Delete. Select. Delete. Okay, good. Back to pen, right? So then, if we have like X is 0.1 and 0, we want to return 0.1, so that's max, right? And if X is -1, then 0, obviously, because it can't be negative. And then duality, like this one must be min. So yeah, okay, good. And then return X, RTN of X, right? Now in BumperCoins, right? Like we have 20 columns and 15 rows, right? Like here, BumperCoins. Let's just play a game with myself. So as you can see here, like we have like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And trust my word, there are 15 columns too. I will forfeit. So you see that right there? There's actually a replay there. Anyways, actually I could just open the replay file. Very dumb replay. Just this coin's moving a bit, I think. But anyways, the point is that like there's 20 columns, right? Which means that the maximum index is what? 19, right? That is if the discretization factor is 1, right? like if you have the 2x2, or let's just make it like in the 2x2 case, right? Like what is the maximum like value for like what's the maximum thing, right? Like for the x-axis, 0 and 1, right? But then in the when we're in the discretization factor of 3, right? Like df of 1, like df of 1, but then we have df of 3, right? So df of 3 would be like kind of like boing, like boing, boing, and like boing, boing, and like boing, boing. And that's sufficient, boing, boing, right? So here, like what's like, you have like 0, 1, 2, all the way to 5, because there's 6, right? 3, 4, 5. So here, this is basically like 6 minus 1. And how do we get 6? Just like the number of columns, the number of calls, times df. That's it. So then like u equals like, and then like parentheses, like u, like another side note, u, like u of x, like u for x equals num calls times df, and of course minus 1 because 0 index, and uy equals, or num calls, sorry, so what am I saying? Num rows. This is rows like that, basically. So that's basically like the whole idea. Just copy that. Okay, so now to actually implement this, I mean, I feel like I could do that later. I mean, I feel kind of tired, but like basically this formula right here, I'm gonna take a screenshot of it after, I mean, well, it's being recorded on YouTube live stream. So I guess I feel like stopping right now because in like an hour, like the sun's gonna go down, so I want to go outside and just get some footsteps in, you know. So I think I'll just stop now. But like this is basically like the tentative. I'm pretty sure this must be correct. In fact, the nice thing is if df is indeed equal to 1, then like this thing just like becomes a no-op, like multiplying by 1 is itself. And again, like multiplying by like basically everything that df basically does, like how we're actually using df in the mathematics in this code, you're just multiplying it by numbers, and multiplying anything by 1 is just identity, like it's a no-op. So in fact, I hope df is 1. I mean, it should be 1, because like connect 4 basically is like 6 by 7, 6 rows, 7 columns. And it took like a week to learn. And like that Sagar's, what's that guy? Like the like this thing, right? Like then like his Othello was like, I know it's 6 by 6. Let me search the number 6. Yeah, 6 by 6 Othello, and that took him I think like 3 days, right? 3 days. So like the dimensions, like discretization factor is 1, obviously in this case, right? It's a 1-to-1 mapping. It's perfect mapping. Same with connect 4, it's discretization factor 1. So like 6 to 6, like a 6 by 6, where I say number of rows by num columns, 6 by 6 takes 3 days. 6 by 7 for connect 4 took me 7 days. I mean, a week. And then like 15 by 20 is discretization factor of 1. And like if we jack that up by like both sides by 3, that'd be like 45 by 60, and like who knows how long that would take. Like the network would have so many much more like complex, like much more, the model size would increase a lot. So like I hope that df is 1 to keep it small as possible. But to make sure that, we have to verify like that, like after doing discretization, like the granularity is sufficient such that like after we launch at 0.4, whatever, like we need to see this happen at least like it should not be this. It should not like map to itself. Like we want to see some progression in each move. Hopefully, I think we do. I mean, one option, actually, yeah, I was reading the AlphaGo paper again, and like not only do they have like image planes for like player, like the current player and the other player, but they also like have like copies of like the previous like k turns for some history too. So I guess like that's how we might be able to encode velocity too. So like we might have to like store like everything for like the current game state, but we may want to also like keep a copy, a historical copy of like the past K, like a sliding window approach, like the past K game states or something. That might be an idea, like something to note. I don't want to think about that. That's just making it more and more complicated model. But anyways, I guess for now I'll just stop, and like the main idea right here is this very nice, kind of very simple formula with some defensive programming too, and like hopefully next time I'll start to actually implement this in code. But yeah, I'll stop now.